Welcome everybody in part 2 of the IR spectroscopy. We're going to solve this question, but before we start it, I just need you to pause the video and read the question carefully. As we can see, these products or possible products have the IR spectrum and the mass spectrum. So we're going to match which of these compounds will match these spectra. First of all, from the first look, we can see that all of these compounds contain OH group, and definitely the OH group is represented in here. But we have to distinguish between the OH. It could come from carboxylic acid or it could come from alcohol. So, does the OH in here come from alcohol or carboxylic acid? If we go to the data table, look at the carboxylic acids. The carboxylic acid comes at 3,300, 2,500. Alcohols have higher wave number. We can notice that the absorbance of the OH peak is too high for being an acid. So it's not an acid. It's either butane 1-ol or hydroxypropanone. So we exclude the first one because we can mention that the OH peak here, the OH peak is too high for acid. Okay, so it's not a propanoic acid. So it's not propanoic acid. Okay, and we have to mention that, how did we know that the OH itself appears? You have to mention like the OH bond, broad band or absorption. Okay, it appears at around 3,400 centimeter inverse. So we exclude the first compound, which is propanoic acid. It's not a propanoic acid at all. We also can mention something else. We notice the presence of this peak, and definitely since it has a strong intensity, it comes between 1720 to 1700, as we can see, and definitely it represents the C double bond O. So we have absorption. We can exclude the second compound, which is butane 1-ol, because it has no C double bond O. So we can mention something else. Technically, the third point that we can mention, that the C double bond O appears at this one, and that's why it cannot be butane 1-ol. And we can also mention something, since we exclude the first one, which is propanoic acid, because of the OH has a low wave number. We don't have the CC double bond peak. We have absence of this peak in this spectrum, and that's why like this is another confirmation that this is not the compound. All right, but now guys, if we want to calculate the molar mass of all of these compounds, calculating the molar mass, it helps you to identify the mass or the molar mass based on the spectrum here. We can see that the molar mass of this compound is 74. And if we calculate the molar masses using the traditional way of going to the periodic table and just calculate as a normal thing, we can notice that the molar mass for the first compound is 74. The propanoic acid has a molar mass of 72, and this one has a molar mass of 74. So we can mention that we have another explanations for excluding this one here because its molar mass is 72. How can I write like the molar mass based on the spectrum? You should mention that M plus, which refers to the molar mass of the compound, has a value, okay, M per Z, mass per charge ratio, is 74, so it could be the first one, which is hydroxypropanone, or butane 1-ol, because it has the same one. So you have to mention that both compounds have a molar mass, or M plus 1, of 74. And as a conclusion, since we exclude this from the first explanation, since it has no C double bond O, okay, we exclude it. We exclude it because the OH is too low for a wave number, and there is no CC double bond absorption. That's why it confirms that the compound is 1-hydroxypropanone. How do we see that thing on the mark scheme? Let's go. As we mentioned, the first point was for the OH. You can see there is OH band absorption at 3,400 centimeter inverse. We also have absorption of C double bond O. It's also mentioned, and that's why it cannot be butanol. You have to tell them like which of these compounds are excluded. And like the third mark comes from mass spectrum, in which you confirm the molar masses using the M plus. It's not only like the MR. And you have to mention something that the most abundant peak has 43, so it could be this and this one. What does this mean? Okay, if we just go to the mass spectrum in here, we can notice that there's the tallest peak in here. The tallest peak indicates that this peak is called the base peak, and it's the most abundant since it's the most stable one. If you look at these compounds, it has a molar mass, by the way, here 43, as we can see. And if we go to these compounds, which of these compounds has a probability of having this peak? Let's see. If we have a fraction from these first three carbons, which means C3H7 plus, it has a molar mass of 43, so it's a possible compound. It was possible compound. If you have a fragment for this compound, you will not end up with such a fragment of 43. And this is a third or fourth reasons for excluding this compound, so it's not included. If you come to this compound and take this fragment in here, you will end up with a molar mass, and that's why you have a probability of having a peak at 43 for both these compounds. We also mentioned that there is no CCD bond absorption at this frequency. You can take this frequency from the data sheet, or you can just mention alternative thing for the same compound, that the OH is too high for propanonic acid. That's why the last sentence, which is confirmation, your compound. Before we start this question in section C, pause the video and read the question carefully. The question says, some diesel cars contain an extra catalytic converter for reduction of nitrogen oxide NOx in exhaust gases. A solution of urea is used for this process. An infrared spectrum of urea is shown. Refer to your data booklet. The question says, draw a circle around the absorption in the spectrum that could be due to the stretching of an H bond. Just keep in mind, you cannot solve this type of questions without using the data booklet. So it has to be given to you, or the data itself, it could be provided within the paper. Let's just go and see the data. I just want to let you know that if we look at the groups in here, amines means like an alkyl group that is bonded to NH2. And for the amides, it looks like C double bond O, and there's an alkyl here and an H2. So urea that we so we have in our question, it looks like C double bond and there is an H2 in here. And urea compound has this part. Okay, now let's go. Which of these frequencies belong to our compound? Definitely it's a 3,500 to 3,140. So this is the first thing. Okay. And if we have C double bond O, and now let's just look at the compound of the amides. Yeah, amides, it appears like if you have C double bond O, it appears like the C double bond O is 1630 to 1700. Okay. Now let's go to the question. The question, since we have an H in here or the NH in here, so definitely this is the NH stretching. The second question says, identify the bond responsible for the absorption at this number. We have this peak in here, and it represents the C double bond O. Now let's take this as an example. Suppose that we have this purefol compound. We can see that it contains C double bond in addition to the chlorine atom. Just keep in mind, we call this functional group here, we call it acyl. Acyl halides, it means that this acyl contain one of the halides. It could be chlorine or bromine. So just keep in mind in your data, you could either have acyl halide, chlorides, or acyl bromides here. Okay, acyl halides and acyl bromides have C double bond R, and we are expecting to have a frequency around 1700. Okay, look at the IR. We have the wave number thing in here. We can see that there's a peak at 1795, and it matches the acyl chloride frequency for the wave number. So this one represents the C double bond O. And if we look at this beautiful peak, definitely it represents the CH stretching. Now we want to refer the fragments in this mass spectrum with respect to this compound. As we learned before, that the first fragment we have is CH3, and it has a mass per charge ratio of 15. So we can say this one represents the CH3 plus. Just guys, do not forget the plus sign. It's really crucial and important. And what about the CH3, CH2? If you just remember the table from the previous class, we can say that it has a molar mass of 29. Either you can represent it in this way, like CH3, CH2, that's correct, do not forget the positive sign, or C2H5 plus, and it's also correct. Now, what about the fragment of 57? What does it represent? If you use your calculator with try and error thingies, you will notice that the whole fragment here has a molar mass of 57. In order to write it in a correct way, you can either write it like CH3, CH2, CO plus, or C3H5O plus. So both are correct. But the question now, what about these fragments? Okay, we can see that we have two fragments. The difference between them is 2, and it reminds us of the chlorine isotopes. If you just remember, the chlorine has two isotopes. We have chlorine 35 and chlorine 37, and the ratio in their heights is 3 to 1. Now we can see that this is a 3 to 1 and this is a 3 to 1. How can I write these fragments, or what do 63, 65 represent? What fragments? If you use your calculator, you can say that it looks like this one here. Okay, but how can I tell like whether it's chlorine 35 or chlorine 37? You can say it's C double bond O, Cl, right? How can I represent in terms of the structural formula? You can say, just let me erase it in order to clarify it well. Okay, it's CO, Cl 35 plus, and it refers to 63 mass per charge ratio. And for 65, it's CO, Cl 37 and plus sign. That's it. And if you look at the whole compound, if you look at the M plus, this one here represents M plus 2, because you know, like the difference between them is 2. So the M plus, it's the whole compound, but with the chlorine 35. I'm going to show you how to do that. The M plus 1 is CH3, CH2, CO, Cl 35. And for M plus 2, it's CH3, CH2, CO, Cl 37. Do not forget the positive sign for both.